Well, in this section, 4.6, we're going to talk about couple moments. Now, a couple is defined as two in equal opposite forces that are parallel, but not collinear. In other words, not lined up with each other. For example, if we have a random object, and if we have a force pulling this way, we'll call that force F, and another force pulling it this way, force F, if those forces are the same magnitude and they're parallel, then we can see that the sum of the forces are equal to 0. But because they are separated by that distance, there is a tendency to rotate in this direction. If there is a distance between them, d, then the moment, sum of the moments is not equal to 0. The moment which is causing that rotation is going to be equal to the moment caused by the couple is equal to the force times the distance. Now, is it just one of the forces or both of the forces? Well, in this case, it is just, you just have to consider one of the forces and the distance between them. In most cases, we have to find out a point of rotation to clearly understand a moment, but with a couple, if you consider this the point of rotation, this force goes through that point of rotation, and the moment then would be this force times the distance. If you considered someplace in the middle as the point of rotation, you'd have that force times d over 2, plus this force times d over 2, and you'd get the same moment, or the same magnitude of the moment. So in both cases, the moment is going to be the force times the distance between those two forces. Let's consider what that might look like. If you have two 30 Newton forces separated by a distance of 0.4, it would be 30 times 0.4, which would be 12. The same thing would happen if you have 40 newtons separated by 0.3 meters. The same magnitude of the moment would be 40 times 0.3. It doesn't really matter if you're pulling on this direction or if you're pushing in this direction. The same distances would be, if you have two forces separated by the same distance, these are all equivalent couples. So we will just put equivalent for all three of those things. Now, couples can be described in our textbook by a couple of different ways. In 3 dimensions, you might see something that looks like this, where there's a little twisty kind of thing. We've talked about those, what those look like, and that would be the direction of the moment or the direction of the couple. In a 2-dimensional drawing, we might see something that looks like this, where again, this is going to be the representation of a couple in a drawing. Couples are free vectors, meaning it doesn't matter where you apply them. You can apply them any place on the object, and they'll have the same effect. And I'll say for now, because in Chapter 7 we have to have some special consideration about that. But for now, it doesn't matter where you apply a couple, it will have the same effect in terms of what happens with the rest of the body. Well, here we have an example problem where we have a couple. Where we have a couple, it's pretty easy to see that this force of 600 is going to be equal opposite of that force of 600. They both have a 30-degree angle with the horizontal, so that they do qualify as a couple. However, it's really hard to see the distance between them. It's hard to see that distance for us to calculate it. So what we're going to do is use Varignon to break it up into their components. Then you can see the distances pretty well. So in other words, this is the force. It has a cosine component and a sine component. This force over here has a cosine component and a sine component. Now you have two couples. You have that cosine component compared with this one, and it's separated by that distance. We have this sine component and this sine component separated by that distance. So when we see that, we can break them up, have two couples, add them together, and we'll get the same resultant couple when we're done. Well, here are some examples of some couples, and I just want to go through several of them here so you can see what they look like. If I had a bar here with some dimensions on it, and I apply a force there of 10 and another force there of 10, if I wanted to find out the moment about point O, I could say 10 times 5, and that's going in that direction, which would be negative. And then I would say this 10 times that 7 would be positive. We add them together, and I can get the moment about point O is equal to 20. Or I can recognize that 10 and 10 are equal opposite, but not collinear, equal opposite parallel, and not collinear. Therefore, they have a couple moment associated with it of 10 times 2, which is equal to 20. So in other words, if you sum the moments about 0.0, you'd get 20, or if you just recognize it as a couple, you get 20. It works the same way. Let's consider these two forces. There we have 10 separated by a distance of 20. It's still going in this direction, and you still get a magnitude of 20 as the couple. It doesn't matter whether you apply it like this or whether you apply it like this. So in other words, we still have 10 separated by 2, and we still get 20. In all three cases, we do the sum of the forces are going to be equal to 0. There are no other forces which would be showing up in our picture, and so the sum of the forces is equal to 0, but there is a resultant moment caused by the couple. If we could look at a couple more here, a little tongue-in-cheek there, it doesn't matter here, again, whether you have 10 separated by 2 or 20 separated by 1. And again, it doesn't matter where you apply the 20, as long as they are parallel. You could apply it right there and right there, or you could put it right out there. In all cases, we get a moment of 20 provided by that couple. Well, let's use what we've learned here to solve this problem. What we've got here are three pairs of forces that are parallel. The first pair that are parallel is this 600, then 250, and these unknown forces are also parallel. In both cases, in all three cases, they are going in the opposite direction, so they are equal and opposite and separated by a distance. All right, what have we got? These 250s are separated by a distance of 1 meter. These two are not, that distance is unknown, so I'll put this distance is equal to L. And maybe we can recognize this as an isosceles triangle because this is an angle 40 and this is an angle 40, therefore these two sides are equal, so let me put this as also distance L. Okay. How do I find distance L? In order to find out what a couple magnitude is, you might need to do some trigonometry. So let's use the sine law here. Well, first of all, let's understand what these angles are. If I have 40 and 40, and then we know the total number of degrees in a triangle is 180, that gives me this angle here is equal to 100 degrees. Now I can use the sine law and compare this over the sine of that is going to be equal to L over the sine of that. So let's do that. 1 over the sine of 100 is equal to L over sine of 40. So L then is going to be equal to 0.6527 meters. Now I can calculate some moments using those distances. Let's make sure we know what we're looking for here. It says the ends of the triangular plate are subjected to three couples. Determine the magnitude so that the resultant couple is 400 Newton meters clockwise. So clockwise going in this direction. So let's see what we've got. What I want you to do is use our convention of counterclockwise is positive. So let's see what we've got. Sum of the moments is going to be equal to, we're going to call this way as positive, is going to be equal to 600 times 0.6527. So that's this one here. It's going in the positive direction. The 250 is going to be going in the negative direction, so I'll say minus 250 times 1. Then the unknown couple is going to be this times this direction, which would be negative. So that would be negative the force times the other distance L, which would be 0.6527. And it says the resultant couple has to be equal to negative 400. Negative 400 because it's clockwise, so that's negative 400. Now I have one equation with one unknown. I should be able to solve that for F is equal to 830 newtons. And that's the answer that we're looking for. So again, it's fairly simple to try to do something like that. We will be using these couples in a variety of problems as we go forward. So it's a pretty important concept for us to understand.